Metal engineering, myself Jijendra. My pin number is 306. My topic is about finite element analysis of tensile property for the single strap butt joint of a carbon fiber reinforced composite. Abstract: to analyze the tensile property for the single strap butt joint of a carbon fiber reinforced composite, a finite element was established using number 22 and 185 material based on LSDYNA with the test data and theoretical solution reported previously. Then the tensile property influenced by three factors were analyzed, that is the connection strength, the failure mode of composite, and adhesive stresses. The result shows that the adhesive interface is zero can be greatly improve the tensile strength and reduce the composite matrix tensile damage. This is the diagram for the structural dimension of a material. Model and material theory. This is nothing but the FE model was established according to the structural dimension and material parameter introduced by Li aluminum 11. The total length of the model is 210 and the overlap length is 101.6 mm. A total of two stacking sequences are set to each composite adherent, which are represented by S1 and S2 respectively. Considering the local effect, the global effect, and the accuracy of simulation results, the thick shell element is adapted to simulate the CFRP adherent, which is divided into four plies in the thickness direction. Each ply is given four angles and four integrating points to define the integrate calculation points and store the calculated result data of each layer. The number 22 material is selected for composite plate, which is convenient to analyze the fiber and matrix damage in a stretching process, while the number 185 material is chosen for the adhesive layer element, which is only suitable for solid element and can simulate the dynamic process of an adherent layer fracture. The model is fully constrained on the left, suffer a uniform velocity of 1.2 meter per second minute per second on the right side. Theory of composite model. This graph is for reversible load. The number 22 material of composite laminate is LSDYNA uses Chang composite. Composite failure theory and stress strain relation is determined the following equation. Three equations. Epsilon 1 is equal to 1 by Young's modulus 1 into sigma 1 minus u1 sigma 2. Epsilon 2 is equal to 1 by Young's modulus 2 sigma 2 minus u2 sigma 1. U epsilon 12 is equal to 1 by g12 tau 12 plus alpha tau cube 12, where even E2 is the Young's modulus of a composite of for x and y direction. Even E2 and E12 are strains in the plane, and S1, S2 and tau 2 are the stresses in the plane, and G12 is the shear modulus in the plane. The equation determines the nonlinear shear stresses coefficient. Meanwhile, the shear failure mode of fiber and matrix is defined that it is the ratio of shear stress and shear strength as follows. Tau is equal to tau square 12 by 2g12 by 3/4 alpha tau 4 suffix 12 whole divided by s square 12 by 2g12 plus 3/4 alpha s to the power 4 and suffix 12, where S12 is the shear strength. The fracture failure criterions of a matrix can be described as follows. F matrix is equal to sigma square by s sigma 2 by s2 whole square plus tau, where s2 is the transverse tensile strength. The failure occurs when F matrix is greater than 1 and material parameters E12, G12, Y1 and Y2 are said to be 0. The compression failure criterion of the matrix L is defined as below. F composite is equal to sigma 2 by 2s12 whole square plus c2 by 2s12 whole square minus 1 sigma 2 by c2 plus tau. where C2 is the tower's compressive strength, and the failure is assumed whenever the F composite is greater than 1 and the material parameters are said to be 0. Then the final failure of mode is defined as fiber. F fiber is equal to sigma 1 by S1 whole square plus tau. S1 is the longitudinal tensile strength. The failure occurs when F fiber is greater than 1 and the material parameters are said to be 0. Parameters means x modulus 1 and x modulus 2, G12, Y1 and Y2 are those parameters said to be 0. A theory of adhesive model. The adhesive element is simulated by material. So the number 185 whose failure theory is defined by Halquist et aluminum 6117, it is a cohesive model only for solid element. In this material, a dimensionless separation parameter is defined to describe the interaction relationship between the relative displacement in the normal and tangential direction. So this the equation is follows for the adhesive element. mm, uh, for displacement in a normal and tangential direction. It is the root over delta 1 by TLS whole square plus delta 2 by TLS whole square plus delta 3 by NLS whole square, where NLS is the maximum separation in the normal direction, TLS is the maximum separation in the tangential direction, D1 and D2 are the tangential relative displacement of the mode 2 loading mode, and D3 is the normal relative displacement of mode 1 loading mode. NLS and TLS are the key values representing the maximum normal and tangential separation of contact surface. The material is in a tensile state when D3 is less than 0, while in a compression state when D3 is greater than 0. A trilinear constitutive relation to be according to can be defined. The constitutive relation is represented in the formula as follows. The formula is about where A1 and A2 A fails are defined by user according to the material actual properties. When failure occurs, the force acting on the element falls to 0 and failed adhesive element is then deleted in the next to load. The formula is sigma max lambda. Tensile stress displacement curve. The board diagram represents the tensile and displacement curve. In first diagram, at zeros, the tensile stress curve raises between 200 and 300 and falls to the displacement near to the 1.4. And second diagram shows that that both are both the curve meet at same point, but the tensile stresses raises to near 400 and displacement falls after the 400. Analysis of mechanical strength. When inputting the material parameter, composite laminates are provided by lithium ET and aluminum 11. However, the constitutive relation of active element is not described as test strain relation. Therefore, the parameters such as NLS and TLS are adjusted when carrying out of FE simulation, and then the calculation result are compared with the tensile stress displacement curve obtained from the test and theoretical solution. Hence, an FE model which is conforming to test the result and mechanical solution can be obtained. This diagram is about adhesive crack layer. Adhesive crack layer. When the comparing the joint strength, the failure mode and the stresses of the adhesive layer under two stacking sequence, the left surface of either end is fixed while the right end is applied with a uniform velocity load. UVL effect of stacking sequence. According to the first moment of adhesive crack, the tensile stress displacement curve of S1 S2 can be obtained, that the maximum stress of simulation result is relatively small, while the displacement value is slightly larger. The joint strength of S2 significantly greater than S1. The simulation result are in a reasonable range which is consistent with a test result. For the failure mode of SSBJ, the adhesive layer is reflected as a transient failure, as shown in the previous figure slide. While the failure mode of the composite adherent is different with a different stacking sequence, the biggest influence factor of the failure mode is the fiber angle contacted with the adhesive layer. When ultimate strength is achieved, failure mode is the fiber angle contacted with adhesive layer achieved. Both the S1 joint and the S2 joint are reflected as a matrix tensile failure, and the failure level of S1 is significantly greater than S2. It is because the fiber angle between S2 joint and adhesive layer is 0, which can maximum bear the tensile load as the failure factor get into minimum. The failure factor of matrix tensile failure can be reflected with a range of 0 to 1, where 1 is completely failure and 0 is non-failure. The both A and B diagram represents the failure of matrix when S1 adherent was fractured. Second diagram represents failure of the matrix when S1 adherent was fractured. The composite adherent of S1 joint is damaged seriously, which agrees with the experimental result through the adhesive stress. The SPBJ is difficult to measure through experiments. The below equation is for the theoretical solution of mechanical model under a tensile load. Under a tensile load, d cube tau a by dx cube plus a1 d tau a by dx is equal to 0. D1 sigma a by dx 1 plus b1 sigma a is equal to 0, uh, where a1 and d1 are the element in the stiffness matrix of unit width laminate constitutive equation. E is adhesive Young's modulus, G is adhesive shear modulus, is the adhesive thickness, and T is the adhesive thickness for the adherent. The general solution for the adhesive stresses as follows, where the corresponding boundary conditions and determine the 7 constant. C is I 1/4 0 minus 6 in the above mentioned expression are represented in the appendix in the paper by L813 at a midpoint of a bounded overlap edge. The adhesive stresses will reach their peak level as follows. So uh, this diagram is about adhesive peel stresses A, and B diagram is for adhesive shear stress. The peel stress and shear stress of the adhesive layer under tensile load can be obtained by using above mentioned equations. As we saw in the previous slide, which shows the peel stress and the shear stress through the overlap position, including both theoretical solution and simulation value. It can be seen that the simulation value is slightly larger and the peak stress of slightly larger than that of H2. Effect of adhesive thickness. The thickness of adhesive layer is also an important factor influencing the joint strength composite. In the study of adhesive thickness, the stacking data of S1 joint is adapted. The adhesive thickness is said to be 0.07, 0.17, 0.47, 0.77 and 1.07 mm, among which 0.17 is the original joint. Illustrate the connection strength of the joint with different adhesive thickness. It can be seen that as adhesive thickness increases, the connection strength increases first and then decreases. When the thickness of 0.17 mm, the joint strength shows the maximum value for the perspective Fe. When the adhesive layer is thin, the stress concentration at edge is large, which causes the crack and adhesive element. When the adhesive thickness is relatively thick, the relative separation of adhesive element increases under shear force. This is the diagram for effect of adhesive thickness graph. Effect of overlap length. The overlap length of upper adherent plate is also an important factor affecting the connection strength and the failure mode. Similarly, the data of S1 are adapted. The overlap length of upper adherent is set to be 95, 101.66, 105 and 110 mm. As the overlap length increases, the connection strength also increases. Therefore, increasing the overlap length can increases the strength of connections structure. This is the table for failure element number. At overlap and upper adherent failure element number. Overlap elements are numbers are 95 mm, 101.6 mm, 105 mm, 110 mm, and the failure of adherent element is 1231 and 1354, 1448 and 1524. Uh, the right side A and B diagram represents the adhesive stresses with different overlap lengths. With increase of overlap length, the peak stress decreases. First A diagram is adhesive peel stress and B diagram represents adhesive shear stress, and the right diagram represents the failure could at fracture movement of upper adherent. Thank you.